Okay, this is the third part of Chapter 3. Here we're looking at exponential and logarithmic equations, and today we're just going to get through the first 3 bits of this here, and we'll finish do the last one tomorrow. Okay, recording. So, looking at this first one here, if we have 2 bases, okay, we want the 2 bases to be the same on either side of the equation. So I'm going to rewrite 36 as 6x, or as 6 squared. All right, that's raised to the x plus 1 power, and here we have 6 to the x plus 6. Okay, this squared, this 2 power, can distribute onto the other power. We multiply powers together when you have more than one of them. So what that gives us is 6 2x plus 2. Okay, so then over here we have 6x plus 6. All right, now exponential functions have the one-to-one property. That means that there's, if you have any given output, there's only one input that would have given them that. So what that means is that you can set the exponents equal to each other if the bases are equal to each other on either side of an equation. So 2x plus 2 is equal to x plus 6. So I'm going to subtract x and I'm going to subtract 2. And that gives me x equals 4 as my solution. Okay, now for this next one here, we got 1/2 and 64. Those are both powers of 2. So I'm going to rewrite 1/2 as 2 to the negative 1. All right, and that is raised to the c power. And then over here, 64, that is 2 to the, let's see, 2 to the 5th is 32, 2 to the 6th is 64, so 2 to the 6th. All right, and then that's the 1/2. So negative 1 times c is negative c, and 6 times 1/2 is 3. So we have 2 to the negative c equals 2 to the 3, so negative c equals 3, and c equals negative 3. Okay, this next one's kind of like the first one. We have 16, that is 4 squared. 4 squared to the x plus 3. Okay, that 4 is going to distribute onto those 2, and then we have the same base. So 2x plus 6 is equal to 4x plus 7. Subtract 2x and subtract 7. All right, that gives me negative 1 equals 2x. So x is equal to negative 1/2. Okay, so this next one here, we've got 2/3. Okay, and on the other side we have 9/4. Okay, so that thing looks like it's been squared, but it's also been flipped upside down. Okay, the 3 and the 4, okay, are on opposite sides. So I'm going to keep this guy as 2/3 x minus 5. All right, and then this one here is 2/3. He was flipped upside down, so that's a negative power, and he was also squared, so negative 2. 3x over 4. Okay, so I want to distribute that negative 2 onto there. Okay, it doesn't actually distribute, it's really just negative 2 times 3/4. Okay, so negative 2 times 3/4 is negative 1.5. I'm going to call this guy negative 1.5x. So x minus 5 here, okay, is equal to negative 1.5x. All right, and so let me add 5, and let me add 1.5x to both sides. 2.5x is equal to 5. Divide both sides by 2.5. All right, and then we end up getting x is equal to 2. Okay, so if you have a logarithm all by itself, okay, which means that we want to isolate logarithms if we can. If you have a logarithm all by itself, okay, you can apply the power definition of a logarithm. Okay, isolate the log. So this guy right here is already by himself. ln of x equals 6. That's base e. So I'm going to pull that base over. Okay, do a little chicken fight here. X is equal to e with 6 up on his shoulders. All right, so we can figure out what that number is in our calculator. Okay, so we got 403.4. Okay, this was a fairly large number. I'm giving just one decimal place here, and that's just to show that it was not a whole number. Okay, I don't really care how big the decimal is, it's just the fact that there was a decimal, it's not a whole number. Later on, we're going to see much smaller numbers, and we're going to want to use a lot more decimal places when we work with those things. So this one, I'm going to need to subtract 6 first. 2 log 5x is equal to 12. And then I want to divide by 2. So log 5x is equal to 6. Okay, common log has a base 10. So if you don't see a base, and it's not ln, if it just says log, in fact, the L and the O look kind of like a 10, okay, that's log base 10, then it's base 10. So 10 to the 6th, 5x equals 10 to the 6th. Well, 10 to the 6th is something with 6 zeros on it, so here's 6 zeros. All right, and dividing both sides by 5 gives me x equals 2 with 5 zeros. Big number. So anytime you have log equal to something, you're going to get a really, really big number. All right, now this guy right here, bring that 8 over, we'll get x cubed is equal to 8 to the 12. Okay, well, I could figure out what 8 to the 12 is and then take the cube root of it, but that might break my calculator. So instead, I'm going to do a little bit of algebra first. I'm going to raise this one to the 1/3 power and raise this one to the 1/3 power. Okay, so raising something cubed to the 1/3 power should cancel it out. This also allows me to just use the multiplication property of powers here. 12 times 1/3 is 4. So this gives me 8 to the 4th, and that's a far more reasonable number. All right, so that gave me 4096. You also could have used your properties from yesterday to bring down that 3, divide both sides by 3, and then get 4. Okay, I don't suggest you do that, though, because if this had been an even power, there's going to be some interesting things that happen with even powers, basically getting pluses and minuses, and you might end up missing that if you were to bring down an even power. Okay, but you're always going to at least get one right answer by doing that. Okay, so here we've got an ln. We don't want a -3, so we'll divide by -3. ln of x equals 8. So x is e to the 8. All right. E to the 6 was a big number. E to the 8 is an even bigger number. Subtracting 4 gives me 12. Dividing by 3 gives me log 5x equals -4. So 10 is the base. Comes up under here. 5x equals, this is a fraction because of the negative power. 10 to the negative 4 power puts me in the denominator, and I have 4 zeros. Okay, 1, 2, 3, 4. 4 zeros. And then when I divide by 5, okay, divide both sides of that by 5, all right, the 5 multiplies into the denominator. Dividing a fraction multiplies in the denominator, all right, which gives me still 4 zeros, but now I've got a 5 in front of it. All right, and then this last one here, we'll just pop that 3 up underneath. X squared is equal to 3, or x squared minus 1 is equal to 3 to the 4th, all right, which is 81. I'm going to add 1 to both sides, so x squared equals 82. All right, that's not a perfect square anymore, but I can still square root it. Plus minus root 82 is plus minus 9.05. Okay, now I need to be on the lookout for any time there was a negative answer that should go inside of a logarithm, because I can't take the logarithm of a negative number. Logarithms only exist on the positive argument side. Okay, now in this case, 9.05 still works. Okay, because plugging in 9.05 here squares it and makes it positive and large, and then subtracting 1 still makes it positive. Okay, so we just want to make sure whenever we get an answer, especially if it's a negative answer, that plugging it back into the original equation will not cause us to take the log of a negative number. All right, sometimes we have to condense our logarithms first. Okay, so So we have a plus right here. That means I can multiply together, okay, the things that were inside. 3 and x minus 2. So log base 4 of 3x minus 6 is equal to log base 4 of x. Okay, well, exponential functions had a one-to-one property. Their inverses are logarithms, so that means logarithms have a one-to-one property. The insides are equal if we say the outsides are equal. All right, so x equals 3x minus 6. We'll subtract x and we'll add 6. All right, so this gives us 6 equals 2x, so x equals 3. Okay, plugging 3 in here is no problem. Plugging 3 in here, I'm subtracting 2, but that still leaves me with 1. Interesting fact, log base anything of 1 is 0. Plugging a 3 in here gives me log 3 equals log 3. Yeah, that makes sense. Okay, the other one did not need to be combined at all. We just need to use the one-to-one property. Okay, so x squared plus 3 was equal to 52. Okay, so x squared is equal to, subtract 3, you get 49. X is equal to plus minus 7. Okay, any problems with plugging in negative 7? No, because I'm squaring it and then adding 3. Okay, so here's another one where they're already equal, okay, or we already have a log 6 equals a log 6, so we just need the two arguments to be equal. 2x is equal to x squared minus x plus 2. We'll subtract 2 from both sides. So that gives me x squared minus 3x plus 2, and that should factor into x and x. All right, and we want something that multiplies together to make 2, adds together to make 3, and both parts are negative. So that sounds to me like 1 and 2. So here's a 1, here's a 2. They're both negative, okay, or they're really both minus. Now, I set each equal to 0, and I get x equals 1 and 2. Okay, so the question is, I know I'm not going to have any problem plugging in 1 and 2 into that one because I'm going to get a positive. Argument. Not quite so sure about this guy though. So when I plug in 1 here, I get 1 minus 1 is nothing plus 2. Okay, that's positive. And then I plug in 2 here, I get 4 minus 2. Okay, that's 2 plus 2. That's also positive. Okay, cool. So no extraneous roots at this point. Okay, last one here. Just got to rewrite this as 4x. And then we can say x plus 3 is equal to 4x. Okay, so 3 is equal to 3x because I subtracted x. X is equal to 1. And yeah, and I'm cool plugging in 1 into each of those things. In fact, plugging in 1 here gives me log 12 of 4. Plugging in 1 here gives me 0, and there I have log 12 of 4. Okay, makes sense. Okay, so now here's where we're going to need our calculators, definitely. You can solve an exponential equation by taking the same logarithm of both sides, okay, and then using the exponential power of logarithms to bring down the exponent. We're going to use natural log. You can use common log if you want, but your intermediate steps won't be the same as mine if you do. So let's all use natural log. So natural log of 4x is equal to the natural log of 13. Okay, that x comes down out front. Okay, in fact, I'll write it again, just so it doesn't look like there's two of them. All right, so 4x, or natural log of 4 times x all over is equal to ln of 13. So I can divide x, and I can divide by natural log of 4, and I can get natural log of 13 divided by the natural log of 4. Let's see what that is in our calculators. All right, so I ended up getting 1.850 right here. Whenever we've got something that's a small number, okay, something that has just one whole number and then a bunch of decimals, let's use 3 decimal places. Especially in this chapter, we're going to want that because a lot of times we're going to have 0 point some numbers. That's going to be a proportion where the first two numbers are a percentage and then the next number is its decimal. So we're going to want to have 3 decimal places for that reason, and also because what we're working with here is a power. Very small changes due to rounding in our answer can have big effects on what kind of thing is outputted when we use that as a power. Okay, now this thing right here, ln of 13 over ln of 4, that looks like the change of base formula. Okay, well what should that equal? That should equal log base 4 of 13. All right, well, okay, so let me see. I'll use x as my variable here. Log base 4 of 13 equals x. Okay, change into power form. So I have 4 to the x equals 13. Well, that's what I started with. Okay, so the solution to that was ln of 13 over ln of 4, change of base formula. All right, so that's why we're able to jump straight from log base 4 of 13 to ln 13 over ln of 4. That essentially is the solution to the equation that we get from setting it up that way. Okay, so then here we have e on both sides. Well, lning both sides when you have e, all right, allows us to bring down that 4 minus 3x times the ln of e. All right, well, that ln of e here, that's ln base e. Okay, that should cancel out and make 1. Okay, cool. It disappears entirely. Okay, so now I just have equals ln of 6. All right, I want to find what ln of 6 is. That's an irrational number. So I need ln of 6. That's 1.792. Okay, all right, so 1.792. So let's subtract 4 from both sides. Negative 3x is equal to that minus 4, which is negative 2.208. All right, and then divide by negative 3, okay, which is negative 0.736. Oh, those negatives cancel out, and that makes it positive. There we go, positive 0.736. Okay, so here's a real straightforward one. 8 to the y equals some decimal. Basically, we're saying what power do we raise 8 to get that decimal? That is literally log base 8 of that decimal. Okay, these are the same equation. Okay, the solution, of course, is going to be y ln of 8 equals ln of 0.165. Okay, I just brought down the y there. So y is equal to ln of 0.165 divided by ln of 8. So if you ever forget your change of base formula, that's okay. Just set it equal to y, put it in exponential form, and then solve by natural logging both sides. And what is that? That is something small probably. ln of 0.165 close parentheses divided by ln of 8 gives me negative. Okay, gives me negative 0.866. Okay, next guy here. All right, we got some uglier numbers. Let's subtract 3.1. Okay, you have to identify, or you have to isolate your base first. Okay, before doing these logarithms, you want to isolate your base. So 1.43 to the a is equal to 5.38. All right, so now I can natural log both sides. I kind of know the drill at this point. Natural log 1.43, that a came down. Natural log of 5.38. All right, so a is the natural log of 5.38 all over the natural log of 1.43. So let's see what that is. All right, so here we have 4.705. Okay, next one here. This one's got an e, so let's ln both sides. I can skip the process of showing the ln over here because I know it's going to cancel. And that gives me the ln of 12, and ln of 12 is just a number. It is 2.485. All right, so if I subtract 2, okay, I get 0.485, and then I divide by 5. And I get 0.097. All right, just to show you how sensitive these things are to how many decimals you use, let's actually try doing e to the 2 times 0.097 plus, or actually not 2 times that, but rather 2 plus 5 times 0.097. All right, let's see if that actually gives us 12. Okay, so I ended up plugging that in, and I ended up getting 12.00001. Okay, so it was important that I use all those decimals there, because if I had rounded it to 0.1, it would probably not have come out to really that close to 12. Okay, so now this is where it gets really fun. You're going to have x's in both exponents, and you have different bases. So we're going to natural log both sides, and we're going to end up with 2 natural logs. We want to just end up with one irrational number. One irrational. Okay, and it's easiest to deal with these irrational numbers when it's the larger, or when you divide by the larger one. Okay, so I'm going to take the natural log of both sides. Natural log of 4 pulled down a 3x minus 1. And then 2x, or 2 minus x, was pulled down from ln of 3. Divide by the larger of those natural logs. 3x minus 1 is equal to 2 minus x. And then ln of 3 over ln of 4. Okay, because the bottom was larger, it should be a number that is less than 1, between 1 and 0. Okay, and in this case, it comes out to 0.792. Okay, so we're in the habit of writing three-digit decimals. Okay, so let's take advantage of that fact and just make sure that it always is a 3-digit decimal. Okay, now what I have to do is I have to distribute that ugly irrational number onto these two things. Okay, so I'm going to multiply that by 2, which is going to give me 1.585. 1.585. Okay, and then minus 0.792x. Okay, so distributing that onto the x's just gives me that many x, because I had minus 1x to begin with. Now what I'm going to do is I'm going to add 0.792x, and I'm going to add 1 to each side. 3.792x is how many I end up with here. All right, add 1, I get 2.585, and then I need to divide. So x is 2.585 divided by 3.792. All right, and I ended up getting 0.682. Okay. All right, so this one here, we know that the powers are going to come down. So just go ahead and write them on the ground there. We got ln 6. We have another thing right here, ln 5. We'll divide both sides by ln of 6. So that's negative 1 plus 1 times ln of 5 over ln of 6. In fact, I don't even want to write another line. I'm going to do divide by ln of 6 right here. Okay, so ln of 5 divided by ln of 6 is 0.898. Right. irrational number, 0.898. Okay, distribute, so negative 0.898x plus 0.898. Okay, kind of convenient for me that I was distributed onto x's and 1's. So x plus 4, or 2x plus 4 over there. I'm going to add 0.898 to both sides. I'm going to subtract 4 from both sides right here. So 2.898x equals 0.898 minus 4. Okay, negative 3.102. All right, then divide. X equals, let's divide by 2.9 or 2.89. Okay, gives me negative 1.07. 1.070 since I'm using 3 decimals. Okay. All right, and so for this last one here, I would like you guys to try to work this out. I've got it written down on, got an answer written down on my little sticky note, so I want to come around and see if you can do it.